Recording in progress.
Okay, so today we're going to finish talking about fluids for now. So we're going to learn the last of our fluids equations, which is what we've been talking about since last Wednesday. So today we're going to continue talking about Bernoulli's equation. And this is a useful equation because this pops up. There's many types of fluids problems that involve Bernoulli's equation. This is a pretty common equation. So we're going to do one example of a problem with that I think is pretty common. Then we're going to introduce the concept of viscosity, which I think a lot of you guys probably have seen before in chemistry, but we'll give a little bit more of a physics motivation for viscosity as sort of friction in fluids. Then we'll derive, or at least we'll talk about how to derive Murray's law, which is a law on sort of optimal transport through flow networks. And then depending on how we do on time, I might say a few things at the end about something that we didn't have time to discuss last week, which I think is pretty useful, especially for the kinds of problems you encounter, which is elastic versus inelastic. But only talk about this if we have time at the end, because I think that this is something that comes up, but is more related to momentum than fluids. Okay. So Bernoulli's equation, for the purpose of this course, is just going to be equivalent to energy conservation in a fluid. It has other interpretations, but I think that this is the most straightforward way to remember what goes into this equation, which is that Bernoulli's equation essentially is an energy balance. Okay, so typical Bernoulli's equation type problem you might encounter might be something like I have some closed, and I'm going to emphasize closed container containing a fluid, which has, in the example I use here, it has a little valve here. So let's say that this is full of fluid. Here are my little fish. And then let's say that this valve at the bottom is open, so there's a bunch of like flow coming out of it. And I'm going to emphasize that the top of the container is closed, because that means that if the container is closed, there's some pressure inside here, which I'm going to call P chamber, which doesn't necessarily have to be equal to atmospheric pressure that's surrounding us all. Because if it's inside a closed vessel, you could pressurize that vessel, so you could have an imbalance there. Okay, so I'm going to put pressure of the chamber up there. And then let's just say that outside the chamber, right, where my flow is sort of getting spewed into, this is still going to be P naught, which we'll recall is just atmospheric pressure. Okay. So this is just the pressure we're all under right now. It's roughly equivalent to the weight of all the atmosphere on top of us. And this can be some number that's a lot higher if I pressurize my chamber. Okay, so then just to sort of finish defining my problem, I'm going to say that the water line in the chamber has some height h. And then let's say that, you know, given this information, I want to find what is v, which is the speed at which water is spewing out here. So given this knowledge, and just how tall my chamber is, can I calculate how quickly water is going to jet out of the bottom of the container? Okay, and let me go ahead and write that as what is V? Okay. So Bernoulli's equation says that energy is going to be conserved everywhere in this problem. So I'm going to pick 2 points that I think are particularly informative, and I'm going to equate effectively energy across those points. Okay. So I'm going to pick as my first point, I'm going to pick right here at the water line. So I'll call that point A. It's just up there, right at the top of the water line within the chamber. And then point B is where we're actually solving for velocity, where the water is spewing out the bottom. And I'm not going to specify anything necessarily about the geometry of that hole there or the radius of that. We just know that, you know, if there's some pressure in there, some height, and some velocity that the water is coming out. Okay, so Bernoulli's equation is going to allow me to equate things that happen at this point with what happens at that completely different point elsewhere in the problem. Okay, so I'm going to start at point A. And at point A, I'm going to write down Bernoulli's equation as the pressure at point A plus 1/2 times the density of the fluid. Remember, that's just kilograms per meters cubed is a material property of the fluid. The velocity of the fluid at point A squared plus rho, again, that's just the density of the fluid again. The gravitational acceleration, h, and we'll say that's the h at A because that could vary throughout the problem. So that just gives me what point A is. And then I'm going to set that whole thing equal to point B, where I'm going to write down those exact same things again. So Bernoulli's equation is going to basically be what allows me to do this equality here, where I'm going to say that all this stuff on the left, which describes the top of the chamber, equals the pressure at point B, so where it's spewing out, plus 1/2 rho VB squared plus rho G H sub B, where H sub B is going to be the height of the water above the bottom of the container at that point. Okay. So I've written this out just purely in symbolic form. So now we're going to simplify this a bunch using what we know about our problem. And we're going to make an assumption here that I think is pretty fair, which is that if I have a really giant container of liquid, it might be shooting out the bottom through some little pinhole or something. So it's very slowly draining. But for our purposes, the water at the top is barely moving, right? If I have like, I don't know, like a kiddie pool or something, and I prick a little hole in the bottom of it, the water at the top of the surface isn't really draining that quickly or moving that quickly. And this is going to come in handy when we do some of our substitutions here. Okay, so let's just go ahead and go through this from left to right. Okay, so the pressure at A, we've said that's just the pressure inside of our chamber. So I'm just going to substitute that out and just write P chamber. So that's just bringing that down. And then because of this assumption that it's draining relatively slowly, we're going to say that the velocity of the fluid up here is actually super tiny. It's effectively zero. Because even though it's shooting out super fast down there, that's because I poked a tiny hole. And so it's draining really quickly out of that little hole. But up here, if I have a giant container, it barely is going to see any change, at least initially. So I'm going to go ahead and say that this is equal to 0. And that's really because of this term being 0. The density is still non-zero. So that's nice. So I can write that as plus 0. And then I have, for this last term here, I'm just going to have rho, which is again the density of water, g, which is on Earth, 9.81 meters per second squared. And then HA, I'm just going to say that that's h because that's how I set it up in my problem. So I'm just going to write that as h, which is the height of the water inside the chamber. Okay, so that's the left-hand side. So now we're going to do the exact same for the right-hand side. So the right-hand side, the water is just jetting out into, the equivalent of the classroom or something. So the pressure is just atmospheric pressure. So I'm just going to write that as P naught, where P naught is going to be 1 atmosphere or some really heinous number if you convert that to pascals, but it's just some constant number at sea level. So that's P naught. Then I have 1/2 rho. And you recall that the velocity at point B is what I'm solving for here, right? So this is actually what I want to know. So I'm just going to leave that in there as rho V squared. And the last question is if I know that rho is constant, that's just the density of water. G is just gravitational acceleration. HB is 0 for the way that we set this up because we have the nozzle down here and the height of the water is there. If you really wanted to be pedantic, you could say there might be some tiny number there, but effectively this is going to be 0 as well. So because of this term, we're going to say that this goes to 0. Okay, so now, we did this whole Bernoulli's equation thing to set up that everything at point A should be equal to the equivalent expression at point B. And then we take that general case and we give the specific case using what we saw in our problem setup. And I'm calling this an energy balance because that's how you derive Bernoulli's equation. But notice that these terms have units of pressure. The reason I call it an energy balance is because that 1/2 rho V squared is the kinetic energy. But really, this has units of pressure, but it comes from the fact that energy isn't created or destroyed in this problem. Okay, so this is my simplified version of Bernoulli's equation for this specific geometry. And so I'm going to go ahead and just rearrange it to solve for V, the velocity that the water is spewing out the bottom of the tank. And it turns out that if you sort of like massage the algebra for a while, you'll get that V, so the speed at which is coming out the bottom there, is equal to a giant square root. That giant square root is coming from the fact that V squared appears down there. And this expression, when you solve this algebra, ends up being P chamber minus P atmosphere over rho, twice that, plus 2 gravitational acceleration h, where h is just this height of the water. And this is going to be the speed at which a fluid exits a closed container from the bottom. Okay, so this is kind of a nice expression because it more or less matches what you might expect, which is that if I have a super highly pressurized container, so maybe I use like one of those soda stream things and I really pressurize this thing, this is going to be a really big number, right? And so in that specific case where P is some huge number, V will also be really large. So if I pressurize the chamber, water shoots out faster, more or less what you would expect. Equivalently, if I don't necessarily pressurize my chamber, but I just have a super tall thing, like I don't know, in the Netherlands, there's this big turbulence experiment that's like a half-mile tall chamber of water. So if I make H really big, if this gets really big, this term also will get big. So the sort of like the limits of this expression, if you think about what happens if you make different numbers bigger, makes sense. Conversely, if I replace the water with, I don't know, corn syrup or something, then rho will get really big. So it'll actually decrease this. And that kind of makes sense because you can imagine if I poke a hole in like a syrup bottle, it doesn't exactly shoot out. So everything about this equation is sort of consistent with intuition, but it's derived just by doing this balance of Bernoulli's principle. And a lot of problems with fluids basically involve setting up this and figuring out which terms you can eliminate, then plugging and chugging to solve. Okay, so this is a general form for the speed of an egressing fluid from the bottom of a container, but there's one very specific version of this problem that comes up quite a bit. And this is the case where you have an open top container. So what about an open top container? So what this would look like if I draw it sort of similar to my problem up here is I have some big container and my little spout down there. And then I just put my water in here. I'll put my fish in there too. And I'm still going to define this as H, and I'm still going to define this is the speed that the water is exiting through the bottom. So the only difference here is that I know that out here I'm at atmospheric pressure, but because the top of this container is open, I also will say that it's atmospheric pressure up there. So in other words, the chamber isn't pressurized, it's just open. Like it's like I have a cup full of water that I poked a hole in the bottom of. Okay, so this is a nice simplification because if I have an open top container, then in that case, P chamber equals P naught, right? The pressure in the chamber is just atmospheric pressure. And so in that case, this term just goes to zero, right? There's no pressure differential between the thing that the water starts out in and where it ends up. So there's effectively no net force due to a pressure imbalance. So that's super nice because then this equation is going to simplify to just say that the velocity of egress equals 2gh. And so this equation, right, is a specific case of this equation, which is itself a specific case of Bernoulli's principle. It just keeps going down. But this is kind of an interesting thing because it says that if I have a big enough container and I poke a hole in the bottom, the speed doesn't care about anything about the shape of that container except the height of it, which is kind of arguably unintuitive. And this is just coming down to the fact that basically everything cancels out except for gravity and the height that the water starts out above. And I'll mention that this isn't true arbitrarily long. For example, if I have a pinhole leak in a kiddie pool, eventually the whole thing will drain, so the water level will actually decrease. But instantaneously, when I first prick the hole at the bottom of the thing, the water level is at H, so I'll get this speed. And then even as the water level starts to slowly decrease due to water leaving the system, this will hold true. It's just that H will be changing as a result. So this is always true in some sense, but you can imagine over a really long amount of time, this H could actually decrease. Okay, and this expression here, the very specific case where equal interior and exterior pressures, sometimes you'll hear this called Torricelli's law. But remember that you can always derive this just from the original Bernoulli's principle, which is arguably the more general equation that you can use in all sorts of weird settings. Okay. So that's Bernoulli's principle in sort of draining containers of fluids. So now we want to change gears and talk about what friction and dissipation look like inside fluids. So what about friction Okay, so viscosity is probably something you've encountered before, and it always has the same definition, but has slightly different interpretations depending on the problem type. But viscosity just captures the intuitive notion that some fluids feel stickier than others, right? If I have something like, I don't know, I guess I was talking about corn syrup or maybe just normal syrup before. If you stir that, it's harder to stir than normal water. And so somehow it feels like the molecules are sticking together more. And viscosity just quantifies how much sort of the molecules in some fluid tend to stick together. And perhaps as you'd expect, this will tell us a lot about how much friction the fluid is experiencing internally as it tries to move. Okay, so remember that the way that we defined a fluid was that a fluid is anything that deforms under an applied shear. So the way that I draw a fluid in sort of a textbook diagram is that I have like some bottom, I have the water surface, I can make some waves there. And I come into the water or whatever the fluid is with my hand. And if I shear the fluid, so I move my hand tangential along the surface, so here I'm kind of grazing the top of the fluid there. Inside a fluid, because fluids are capable of deforming, what'll happen is the velocity right at the surface will be some relatively big number v. But then as I go deeper into the fluid, the velocity was going to drop off. And so like a fish here will feel like something crazy going on, but a fish here will barely notice anything happening. Okay, and let's say that the depth of our fluid is something like d or something. Okay, so this is our textbook definition of a fluid, is that rather than the entire thing moving like some rigid object, really just the top layer moves because it gets sheared by my hand. Okay, it turns out that when I push my hand across the surface of the water, as you might expect, I'm going to encounter a little bit of resistance, right? If the fluid is, water, I might encounter a little bit of resistance, but presumably if I have a tank full of, I don't know, syrup or something, it's going to be a lot harder to push my hand across the top. So viscosity is going to quantify how much resistance the fluid exerts against a shear as I try to apply one to the surface of the fluid. Okay, so the formal definition of viscosity, and I've never seen this come up except in very specific cases, but just so you see what this looks like, the formal definition of viscosity is if I'm applying a force F with my hand, so F here is just the force I'm shearing on the surface, the amount of sort of resistance I expect to encounter should be equal to the velocity, right? So the faster I go, the more force I encounter. Where A is going to be the cross-sectional area of my hand. So, if I have bigger hands, I guess I feel more resistance at the top. And then you usually use the symbol eta to note viscosity. So this is how I draw the Greek letter eta. I'm sure that, Wikipedia has a much nicer way of drawing that. And then all of that is divided by d, the depth of the fluid. So in other words, the deeper the fluid is, the less overall resistance I'm going to feel to the shear I'm applying. And that's due to sort of that's due to sort of boundary effects. Okay, so this is the formal definition of viscosity. And I'll just write out what these terms are. So let's say that this is force, this is depth, which is just distance. A is the area, in this case is of my hand, and V is just the speed at which I'm shearing. And this relationship implicitly defines viscosity in terms of these properties. Okay, so viscosity, importantly, viscosity eta is a material property. So just like whenever I see, rho in some problem, I know its density, and density for the purpose of this class is not usually changing, at least for fluids. And for viscosity, viscosity is usually just some constant where, syrup has some viscosity, water has some other viscosity, and some very special substances like superfluid helium have effectively zero viscosity. Okay, so viscosity is just sort of intuitively captures how much material resistance a material exerts, and we can even derive its units just using dimensional analysis. So if I wanted to define viscosity, or if I wanted to calculate viscosity by doing an experiment, I could just do a shear experiment, measure everything in this equation, and then solve for whatever is left over. So the experiment might look something like rho equals FD over speed A, where all that this equation is just me rewriting this in terms of eta. And there are these fancy devices called rheometers that quite literally do this calculation. They apply some known shear to some fluid and they measure all of the relevant properties like the velocity. Yeah, what's up?
What's the difference between shear and force?
So shear here is just a force applied along the surface. So it's just specifying that I'm not like smacking my hand into the fluid or something. It's just along the top. So it's just a type of force, I guess. Okay, so rheometers implicitly are going to do this calculation where they apply some known force, they observe the resulting velocity or speed, really, and then these are just material properties of some apparatus I build. Okay, so if I want to find the units of viscosity, I'm going to use my square brackets again to denote this. So square brackets of eta, those equal, square brackets of force d v. And I'm just going to go through them one by one, substitute in for everything. So this is going to equal, I know that force is 1 Newton, which is equivalent to a kilogram times meters per second squared. That's F equals ma. So I'm going to write that as kilogram meters over second squared times meters, right? Because d is just the depth. V here is speed, which is meters per second, and then a is just meters squared. In terms of if I, rearrange those units extensively and I cancel out all of my repeated terms, I'll basically just get that the units of viscosity are kilograms over meters times seconds. This isn't a particularly elegant unit, but this actually ends up being equivalent to writing pascals times seconds. And if you look up tables of viscosity in chemistry textbooks on Wikipedia or something, usually you'll see it measured in Pascal seconds, which is just the SI unit, which is effectively equivalent to this. So viscosity is units of pressures times time, which I don't have a great intuition for, but it's useful to know, especially when you're checking your units and calculations. Okay, so that's viscosity. It's a material property, and it affects how much a fluid is going to resist applied loads. Okay, so the reason that it's useful to know about viscosity is we can use it to calculate things like how much power or how much energy is dissipated when I try to move a fluid. Okay, so very common context in which you encounter fluid flow. This is especially true in biology because of our circulatory system, but even our very wealthy colleagues in the petroleum engineering department encounter this problem quite a bit as well. And this is moving a fluid through a tube or a cylindrical vessel. So I'm going to write cylindrical tube flow. Okay, so if I have some cylindrical tube, so I'm just going to draw it like this. It's a cylinder, so it has circular end caps, but I'm going to try to draw that in perspective. This is the span of the tube. A typical way that I force a fluid through any sort of tube or through any sort of channel is by applying a pressure gradient. So if I have some cylindrical tube, I normally will have some pressure on one side and then some other pressure on the other side. And I'm just going to specify that this tube has some radius. I'll make it easier to see, so I'll write that in a different color. I'll say that some radius r that we'll assume is just fixed for now. Okay, so typically if I want to force fluid through a tube, I need to have PA greater than PB. And because that implies that there will be a force to the right. And if you want to prove that to yourself, remember that pressure is just force over area. So if I have a pressure here, I have a pressure here. I have some fixed cross-sectional area, so that's not going to change between the two sides. So this pressure here exerts a force that way. This pressure there exerts a force that way. If PA is greater than PB, the one on the left-hand side wins, so the fluid should move overall to the right. And I'm going to write that as B. Okay. So if I'm driving a fluid through a cylindrical vessel, a cylindrical pipe or something, it turns out that if I go and I look at what the fluid particles are doing, not all of them are actually traveling at the exact same rate through the pipe. So if I go and I measure the cross-sectional velocity or the cross-sectional speed through the flow, usually the way it looks is that I have fluid near the wall barely moves. It's called a no-slip boundary condition. But as I get closer, to the center, I'll see that the fluid moves more and more. So in other words, transport through a pipe isn't just the entire fluid moving as just one big plug through the pipe. Really near the edges, it kind of gets stuck because it's feeling a lot of friction from the wall. But then as I get more towards the center, the flow will move a lot faster and it has some overall rate at which it's going through. And the intuition for why that happens is if you look at how I define shear up here, you'll notice that the amount of friction force I encounter depends on the depth. And so this bottom surface affects how much resistance I feel against shear. So if I'm trying to drive a flow through a tube, effectively, the closer I am to some wall, the more friction I feel. And so the fluid near the edges tends to move a lot slower. So, I can move fluid through a pipe, but it's not all moving uniformly. Really, the center is sort of moving faster. What's up?
Is there any sort of like normal force or friction force that's like along the walls of the container, or is it just like inside through tracks?
So for our purposes, there's and we're gonna do an idealized version where the flow doesn't have any components orthogonal, but there is drag force along the wall. That's effectively what causes there to be a lower velocity near the edges. And this assumption that all the flow just moves along the span, this is called laminar flow, which you might have encountered in other contexts before. Okay, so I'm gonna write that my pipe has a length. I'm going to use curly L for this, just because your book likes to use the curly L. Okay, so if I have a pipe like this, I can calculate the flow rate. And I'm going to use the letter Q, which is what your book uses, I think, because they ran out of other letters. So Q equals flow rate. And usually if I'm trying to, I don't know, move petroleum in West Texas or whatever, I'm interested in how much fluid I'm moving per unit time. So the units of Q, the flow rate, are just equal to meters cubed per second. So what volume of fluid am I pumping across that pipe every second that passes? Okay. So I won't derive this because I think that the derivation is pretty insane. So I'm just going to show this, the equation here, but we'll talk about what it means. So for a pipe with laminar flow, the flow rate Q is given by PA minus PB. So I'm going to put that in brackets, times, and this is going to be a lot of symbols, but and that's why I don't like this derivation, pi r to the fourth divided by 8 eta, remember that's our viscosity, times L, where L is the length of the pipe. So I'm going to put this whole second expression in brackets. Okay, and this is flow rate through, and importantly, I'm going to write cylindrical pipe. And the clue of this cylindrical is I have a radius and I have a pi, so clearly something funny is going on there. Okay, so what does this equation tell me? Okay, so yeah, what's up? Oh yeah, that's a 4. Let me draw a little bit clean. Yeah. Okay, so this expression, the derivation comes from derived via force balance between the pressure gradient and friction due to eta. But actually solving that out, I think your book does do it, but I don't think it's super elegant. But this expression itself is somewhat intuitive, right? So if I have some pipe and I don't actually apply any pressure differential, so this is equal to 0, then I shouldn't get any flow. And that makes sense because you can imagine if I just have a tube that's full of water, right? The water is not going to flow left or right unless I do something to it. So that should make some sense that that term expresses here. This term is a little bit weird, but dimensionally it kind of makes sense, which is that if I have a big cross section, I should move fluid faster, right? Because I'm literally pumping more plugs of fluid through. Equivalently, it stands to reason that if I want to move as much oil out of West Texas as quickly as possible, a little tiny pipe is going to move it a lot slower than a giant pipeline. So this r to the fourth ends up telling me that as I increase the radius, I get really, really dramatic increases in how much flow rate I can get. So there's a huge incentive to increase my pipe cross section if I'm trying to get the biggest flow possible. Conversely, though, if I'm trying to move at a really long distance, then that will decrease my flow rate due to the aggregated effects of friction. So in other words, the longer distance I'm trying to pump that fluid through, the less overall flow rate I expect to get because I've just encountered so much shear resistance along the length of that pipe. So it's harder to pump things longer distances. And then the other thing that makes sense here is that there's viscosity in the denominator. So big viscosity has low flow rate. And that makes sense because presumably if I'm trying to pump, I don't know, maple syrup out of, I don't know, the maple syrup factory, that's going to be a lot more expensive and difficult to do than something like water. And in fact, a big thing that people in petroleum engineering study is whether you can add things to oil to basically lower its effective viscosity. So people dump polymers and all sorts of weird stuff into oil just in order to make this equation maximize this. Okay, so this is the equation for the flow rate Q in terms of a pressure differential times a bunch of properties of my pipe and my fluid. So this is usually something I can control by just, increasing how much pressure I apply at my front end. But a lot of this is usually something that's external to my problem. I have to pump oil, so I'm stuck with this, and my geometry is set by whatever my manufacturing tolerances are. I mention that because sometimes you'll see this equation written equivalently as Q equals delta P times G, where this quantity G is called the conductance of the pipe. And in the specific case of a circular cross-section cylindrical pipe, G just equals this pi r to the fourth over 8 eta L. Okay, so this version of the expression is nice because this is actually a little bit more generic, which is that a lot of different pipes of different shapes and sizes and what have some different value of G. And so this just tells me that flow rate equals pressure drop times some properties I don't necessarily know that much about. Okay. Yeah, and I'll just mention that, you can check this yourself, but if you were to do the whole units thing on G, you would get these really sort of ugly units of meters to the fourth, kilograms seconds, and you can derive that just by going through that term. You have to use the fact that this is Pascal times seconds. Okay, so that's the equation, that's flow, and this equation here, it bears a non-trivial similarity to Ohm's law, which some of you guys might have seen in E&M, and there ends up being pretty good reasons for that, where you can think of pressure as maybe a voltage drop and Q as current or something. Okay, so the idea of conductance is useful because it allows us to maybe assess what happens in more regular geometries other than simple pipes with laminar flow. Okay, so conductance. Okay, so if I have some really weird shaped pipe that isn't just a perfectly uniform cylinder, it might have something like a sort of funnel or constriction inside of it. So maybe I have a pipe that looks like this, but then it sort of tapers to some smaller radius. And it could be that I designed my pipe that way, or I could just have like buildup or some obstruction that effectively reduces this radius. And let's say that the pipe has some initial radius, I'll call that RA, but then at the constriction, it has some new radius RB. And we're gonna say that RB is less than RA. So the idea of conductance gives me some intuition for what I expect to happen inside my pipe, which is that I know from up here that G goes as R to the fourth. Nothing else has changed here, so I'm gonna go ahead and say that GA is proportional to, I use that sort of fish-like symbol to know proportional to, similar to your book. That should be proportional to RA to the fourth. GB is proportional to RB to the fourth. And I mention this because this is a very common genre of problem where it'll tell you your pipe went from this radius to that radius. If let's say that RA equals 1/2 RB, this tells me that the difference in flow should be something like G B equals 1/2 to the 4th GA. So without even having to know everything about this equation, if I know that this conductance is proportional to radius to the 4th, I can do these problems that just tell me that one thing changed. And we've seen a couple of problems like these before. I know that with the Kepler's law stuff, they use these kinds of proportionalities all the time. But this is a whole genre of problem where they'll tell you that your radius went from this to this by some fraction, and you basically have to just propagate it through and see how it changes. And the important thing is to remember what the scaling of the one thing that changed was. Okay, and the big takeaway here, right, is that I only have my radius, but I got a really dramatic decrease in my conductance, and thus I should expect any flow rate to decrease as well. Okay, so conductances are a useful thing because we can actually add them and combine them together for pipes in a way that's actually extremely similar to the way that we do this with resistors and electromagnetism. Okay, so conductance of pipes in series. Okay, so I have this overall weird shaped object here that has some radius here and some radius there. Let's say that I'm building some crazy pipeline system. I might be interested in knowing what is the overall conductance of this combined element, right? Because maybe I'm trying to design my pipeline and I don't really care that much about what happens here. I just want to know overall how this one unit interacts with my whole thing. So in this case, I have flow that's going first through this and then through this. And so I would call these in series because first the flow sees this and then the flow sees this. So it first sees the big cross section, then the little cross section. So in this geometry, in the derivation of this, I didn't think was very illuminating. So I'm just going to show this equation, but the book gets into how you derive it. The overall conductance of the pipe effectively is equal to this expression, which is a lot like what it looks like when you add resistors in electrostatics, if you've seen that before. But basically it says that this is basically called the harmonic sum, where you basically add the reciprocals of your other two quantities. So if I know this, which is just proportional to that, I know this, which is proportional to that, I calculate each of these quantities, I take 1 over each of them, and then that equals 1 over the overall conductance. It's a little bit confusing. If I was a little bit nicer, sometimes it might be better to just write this as G all equals 1 over GA plus 1 over GB, all that to the -1, just so you actually have this cleanly written out. But importantly, this tells you that you have this sort of unexpected scaling where your conductance, if I really quickly increase or decrease one of these, this will dominate this sum, and so that will dominate the overall thing. So in other words, your conductance is sort of affected by whichever one of these is larger or smaller when you add conductances in series. Okay, so this is conductances in series because the flow first starts out and goes through that, but then later it has to go through that. So it does this, then that. That's usually what series implies. But there's also the cases where I can have pipes that are in parallel to each other. So I can have cases where I have conductance of pipes in parallel. So this would be some problem where I have something like a branching flow, where I have some pipe that then goes to some sort of weird diverging structure, where now my flow starts out here and then some of it goes to the bottom, some of it goes to the top, and it sort of is splitting across the two things. Okay, so in this case, I have what I'm going to call conductances in parallel, because I have some GA here, I have some GB here, so I have some conductance associated with the upper branch, I have some associated with the lower branch, but importantly, particles of flow are simultaneously going through either one. So there's none of this, I don't go here then here if I'm a fluid particle, I either go to the top or the bottom. And flows that particles that start out here sort of get evenly divided across the two. So that's the difference between series and parallel. Is parallel, you always do stuff in parallel. Okay, so in this case, if I wanted to find the overall conductance of these two parallel pipes, In this case, the expression is way, way simpler, which is I just write that the overall conductance just equals GA plus GB. And I'll go ahead and just box these so it's a little bit nicer. Okay, and these are the only two cases that you might encounter, but I just will emphasize that if you've seen these resistor networks problems that come up a lot in electromagnetism, this is almost the exact same type of calculation where here I have two things in parallel, so I add these two things. Here I have two things in series, I go from one to the other, so I add the reciprocals. And those are the two geometries. I've never seen this come up, but you could imagine designing some really sort of complex flow network where you have things that are in series and in parallel, and it gets really out of hand. And so then you'd have to combine these rules systematically to build the overall conductance. But generally, you won't see that often. In electromagnetism, there are crazy resistor network problems, but usually we don't see that with pipe problems. But it's worth knowing that these two rules can be combined to form arbitrarily complicated pipe networks if needed. Okay, so the reason that I really like talking about the conductance so much is because the conductance ends up being how we estimate how much energy overall is dissipated while I'm trying to pump my oil through some pipeline or something like that. So we can use the idea of the conductance to motivate finding the power dissipation of a pipe flow. Okay, so if I have some flow through some channel, and that flow has some rate Q, where again, Q is just volume per second. It's how many liters or how many meters cubed of oil I'm pumping per second. If that pipe has some geometric property, the conductance G, which is primarily set by geometry, it does depend a little bit on the viscosity, but usually that's just set by whatever fluid we're working with. The power dissipation is going to equal the flow rate squared divided by G, the overall conductance. And I'm just going to put this funny little like underbar in my P to help differentiate it from the P for pressure. Okay, so this is going to be power. This is going to be the flow rate. And this is going to be the conductance. Okay. So this tells me a couple of things. The biggest one is that if I'm trying to move a ton of fluid through a pipe, the more fluid I move, the more power I'm going to have to expend. So whatever my generator I'm using to build my pump that sort of forces the fluid through the oil pipe, the amount of power I'm going to have to dump in is going to increase super quickly. And this is what makes it so expensive to move large amounts of fluid long distances. And it scales quadratically, so it's a very sharp increase. However, if I'm able to reduce the resistance of my pipe or equivalently increase the conductance, I can decrease the power. So generally speaking, if I want to move fluid as quickly as possible or for as cheaply as possible, usually my flow rate is set by however much I have to move at a given time. But this is usually what I want to get to be as large as possible. Okay. So I don't think we've talked about power yet, so I'll just mention what this can be interpreted as. So if I go ahead and I do the whole, unit analysis on this, so I'm going to put that underbar there. I won't get super beautiful units here. It ends up having something like I have to do the units of Q squared divided by the units of G. And insanely enough, I believe that gives you meters to the sixth because it's meters cubed squared over second squared. So that's just me squaring. This term gives me these awful units. And then on the bottom, I get meters to the fourth seconds over kilograms. So not the most elegant units I've ever seen. Turns out that if you plug and chug the units out through this, you'll actually get that the units of this quantity are kilograms meters squared over seconds cubed, which is actually equal to the units of energy over time. So joules per second, where joules is SI units, which is equal to W, where that's a watt. So power here is measured in watts, just like power that we encounter every day. I have a 60-watt light bulb, or at least I used to. And so you can actually equate, the literal amount of energy per time you're going to have to dump into your pump or whatever in terms of very physical properties of your pipeline. So this is energy over time is how we should interpret this. So let's say that's energy per time. Okay. And the reason and where this power is coming from is the fact that when I'm trying to force the fluid through the pipeline, I encounter friction. That friction is due to the fact that the water sticks or the oil or whatever sort of sticks to the walls of the chamber. And so that friction is what makes it hard to pump the fluid through. If I had something like, superfluid helium that has no viscosity, it would require no power. It would just be an energyless transport. But in the real world, we're sort of stuck with the fact that we have to encounter viscosity. Okay, so then one thing that your book has a whole section on this because I think it's particularly relevant to biomedical applications. Although I'll admit I work in non-biomedical fluid dynamics. I've never seen this come up in other contexts. But when you use this idea of conductance and power dissipation to think about the human circulatory system, sometimes you encounter this concept called Murray's law. So Murray's law describes branching flow networks. So if I have something like and because I think this is particularly relevant to the circulatory system, we'll use a red fluid for Halloween or whatever. So I have some branching networks, like, I think that our circulatory systems are more or less a fractal where you have these large vessels that divide into smaller vessels and they sort of branch out like a tree. Murray's law says that if I want minimal power dissipation in a flow network, then I need to satisfy the following condition. So if I have a starting radius, so I'm going to just call this big R, and that's going to be the diameter of a blood vessel or some pipe before some bifurcation. And that splits into two new vessels, which have RA and RB. So the big pipe splits into two new pipes. If I want to have minimal power dissipation, so I want to do that as efficiently as possible, I want to balance my conductances as such as to avoid paying as much of this cost as possible, then the following condition needs to hold. R cubed, so the radius of the big vessel, should equal R1 cubed plus R2, I should use RA and RA cubed plus RB cubed. If I want efficient transport. Okay. With minimal. Okay. So this expression is not a law in the sense that, if I'm some petroleum engineer or something, I can pick whatever radii I want for my network, right? Like this doesn't have to be true. I could pick RA to be giant or something like that. However, if I want to somehow minimize the total amount of friction I encounter, generally I want this to hold. The book gives the derivation. It's pretty elaborate, so I think it was a little bit out of the scope here. But importantly, it turns out that as humans, we're pretty highly evolved. And so over the years, our circulatory systems have sort of learned about what maximizes the flow rate while minimizing the resistance. So it turns out that in real circulatory systems, Murray's law usually holds. So this law holds for a lot of biological settings due to evolution. All right, thank you.